evening. Thank you all for coming. I'm Rick Carlson. I'm the director of the Department of Terrestrial Magnetism, one of the two departments of the Carnegie Institution for Science that's on this campus. Does it work? Okay, then I'll just yell. Technology. I can speak loudly. So, welcome. This is the second in our series of neighborhood lectures. Today I'm pleased to be able to introduce Conel Alexander, who's been a staff scientist at DTM for 24 years. Something like that. We don't. After 20, you don't count anymore. So Conel got all of his degrees in his home country of England, a bachelor's at Open University and a PhD in experimental physics at Exeter University, and then came to a place that many of you probably don't recognize, at Washington University in St. Louis, a small private university. But you would know this if you were into the fields of cosmic chemistry and meteoritics, because it's one of the leading areas in the world in this topic. So we were lucky enough to attract Conel away from Washington University, 1994, I believe it was, brought him here as a staff scientist ever since. Conel is a fellow of the Meteoritical Society, and if you saw his quote in the Washington Post after the March for Science last weekend, that's Meteoritical Society, not Meteorological Society. So no questions tonight about climate or weather or anything like that. It's about meteorites. So I'm very pleased to be able today to introduce Conel, who will speak on rocks from space, be grateful and a little bit afraid.
Thank you for coming, everybody. So in this talk, I'm hoping that I can persuade you that rocks from space, both big and small, have had a profound effect on the evolution of our planet, and actually have generally been fairly good to human beings as well. I've also, since I've spent almost my entire career studying meteorites, I hope I can persuade you that meteorites are a fantastic scientific resource, being able to address questions such as how the elements were built up in stars and the galaxy, to making solar systems and habitable planets, and maybe even the origins of life. Hopefully I'll have time to cover all of those subjects. So, of course, people have been fascinated with meteorites long before I came, and in fact, even before meteorites were recognized by modern science. We certainly know, for instance, that the ancient Greeks and Romans venerated meteorites, presumably because they were gifts from the gods. Also, for many societies that didn't know how to make iron, they were used for making jewelry and tools. The earliest examples of that I know of are about 5,000-year-old beads from Egypt. A little bit.
Something you made up, Mary. I mean, they didn't know that it was from
Yes, they did.
the sky.
Yes, they did.
And they actually wrote that it came from the sky.
Yes, this is a.
It wasn't until the 1700s that
That's not quite true. In fact, going back into the 5th century BC, Greek philosopher Diogenes said they came from the sky. Nobody believed him, but now he has a group of meteorites named after them.
some Egyptians thought that.
Absolutely, this was the hieroglyph for iron from the sky. And in fact, so this, about 3,300 years ago, Pharaoh Tutankhamun was buried with a dagger, this beautiful dagger that's made out of an iron meteorite. And I should say that Native Americans, Inuit, also used iron meteorites to make tools and beads or jewelry. And in fact, I'm told that they can be used to map out trade routes in North America. So the first well-documented fall of a meteorite, at least in Europe, was the Enisheim meteorite in 1492. It fell in November, about a month after Columbus had discovered the New World. This is a part of the Alsace region, which is now France, but in those days I think was German. At the time, Maximilian, the heir apparent to the Holy Roman Emperor, heard about this meteorite. He was in the neighborhood, declared that this was a good omen for his forthcoming battle with the French, which he duly won. So, he'd ordered that this meteorite be kept in a church nearby. It was chained up to a wall just in case it decided to leave as fast as it had arrived. Since then, the church has fallen down, but the meteorite still exists and is on display. But despite the fact that this clearly the meteorites clearly have some divine importance, it wasn't recognized for another 300 years that meteorites came from outside of the Earth, or that they were scientifically interesting. And in fact, in the halls of some unnamed funding agencies, that's still the case. So why should we be interested in meteorites other than the fact that they're from space? I think the most obvious thing is that they're very old. They've come from bodies or planetesimals that formed in the first few million years of solar system history. So if we can decipher them, and that's the trick, that's the big if we can decipher them, they can tell us a lot about how the solar system and the planets formed. Now, there's a bewildering range of meteorites and meteorite names, and I'm just going to ask you to try and remember 3 basic types. Now, for reasons that I'm going to come back to later in the talk, early in the solar system history, there was a lot of radioactivity around. And so that when you make a body, there was a lot of heat given off. If a planetesimal formed within the first 2 million years of solar system history, it melted and differentiated into what we now know as iron meteorites and into rocky mantles, which any terrestrial geologist who studies volcanic rocks would recognize. If those planetesimals formed after about 2 million years, they didn't melt. And these are the chondritic meteorites here. And these are made of the dust that was floating around in the disk around the young sun. It's a very complicated mixture of materials, and which is why it's taken us a long time, 200 years at least, to start deciphering this material. And one of these objects, one of these types of objects, these high temperature inclusions, have been dated, are the oldest objects we know of in the solar system. And they are basically our T0 for the start of the solar system. So that's 4.567.3 plus or minus 0.2 million years. I don't expect you to remember that, but it's always impressive to see how precise people can date things these days. Now, there is one particular type of meteorite that's really very important to geochemistry, and that is the CI type of chondrites. These have compositions. Here I'm comparing the composition of the sun to the composition of the CI chondrites, and you can see they're almost identical within the area. I haven't put the uncertainties here. Within the uncertainties of the measurements, they are identical. At least to the rocky portion of the sun. That is the sun without the hydrogen, the helium, and things like nitrogen, carbon, and oxygen that at least partially stay in the gas phase. So since the sun makes up 99.9% of the solar system, presumably everything we now see today ultimately evolved from this composition. And so this is the ultimate reference to which most geochemists and cosmochemists will compare their compositions. And we'll see an example of that later in the talk.
That's the original cloud composition.
This is presumably is the original cloud composition, yeah. And the reason we often use the CI chondrite compositions and not the solar compositions is because we can measure them more precisely than the solar composition. So where do meteorites come from? Well, some come from Mars, some come from the moon, but the vast majority are thought to come from the asteroid belt. The asteroid belt is between the orbits of Jupiter and Mars. These green things are the main belt asteroids. The red things are the ones you should be more worried about. They're in Earth-crossing orbits. What you can't see is, so how do you get from the asteroid belt into these Earth-crossing orbits that ultimately the Earth will sweep up? What you can't see in this figure, but you can see more easily when you plot the number of asteroids versus their distance from the sun here in astronomical units, where astronomical unit is the distance from the Earth to the sun, or about 150 million kilometers for absolute numbers like that. And what you can see in the distribution is these big, deep holes. And these are resonances, primarily with Jupiter, but also Saturn is important, resonances with the orbits of Jupiter. So an asteroid that's sitting here would go around the sun 3 times to every one time that Jupiter goes round. And every time this happens, they get a kick. And then they get into increasingly eccentric orbits, and that will eventually end up intersecting the orbit of the Earth. And so asteroids will drift in from these regions via various mechanisms into the resonance, and then get scattered over the course of a few million years into Earth-crossing orbits, and the Earth sweeps them up. Or they get sent out of the solar system. And so this long suspected connection between the asteroids and meteorites has been confirmed now by 3 spacecraft missions. 2 missions have have demonstrated that the long-thought connection between the most common S-type asteroids and the most common ordinary type chondritic meteorites. The recent Dawn mission to Vesta has demonstrated that it is indeed what we suspected was the source of the so-called HED achondrites. We have 2 missions that are ongoing at the moment, but one Japanese, one NASA, that will be bringing back samples from quote-unquote more primitive meteorites in about 2020 and 2023, and we hope here on campus to be heavily involved in the analysis of those materials. So where do we get our meteorites? Because space missions take a long time, they're very expensive, and don't always work. So we get most of our meteorites from deserts. Arguably, and this is because the meteorites tend to weather slowly there, and they accumulate over time. Arguably, the best place to find meteorites is Antarctica. You wouldn't normally think of it as a desert, but it is. The snowfall is very low there, and it's very cold, which preserves things very nicely. And Japan and the US have had long-term collection missions in Antarctica. And this is my colleague, Larry Nittler, risking frostbite as he's bagging and tagging a meteorite on one of these, the NASA-funded expeditions. Another great place for finding meteorites is North Africa, in the northern Sahara. Places like Morocco, Algeria, Libya, Tunisia. Obviously, those are not places you can generally get government-sponsored expeditions to go to. So that is the area where commercial dealers rule. And in fact, the locals have become very good at finding meteorites. And they have a good incentive because meteorites, the rare ones in particular, can be up to $1,000 a gram, so more expensive than a meteorite, which to somebody in North Africa is an awful lot of money. But unfortunately, even if you're lucky enough to go on these sorts of expeditions, you don't get to keep the meteorites. As soon as they're bagged and tagged, they go into a box and they become NASA property. So unfortunately, we meteoriticists generally lead a much less glamorous life than explorers like Larry occasionally get to do. We write begging letters to curators at museums and the Johnson Space Center where the Antarctic meteorites are curated. And if we're lucky, we get a meteorite in the mail. So we spend most of our time in windowless rooms playing with expensive and very temperamental toys. It's actually a lot of fun, but it's not quite as glamorous as being out there in the deserts, Antarctica or the Sahara looking for meteorites. And this is just the rogues gallery of the current meteoriticists on campus. I haven't included Rick because he has a much nicer smile than the rest of us. So of course, we don't always have to go looking for meteorites. Sometimes they get delivered to us. And the most spectacular recent example of that was in Chelyabinsk, Siberia in 2013. I'm sure most of you heard about it at the time. But what you're going to see in these videos is and I should say that it's the perfect place for a meteorite fall to happen because everybody has dashboard cameras. And what you're going to see is 3 views of this meteorite coming in. So it's a 60 foot across lump of rock, about 10,000 tons. It's coming in at about more than 40,000 miles per hour. It has the kinetic energy that's equivalent to about 30 Hiroshima bombs.
Why
So
do Russians in that area have dashboard cameras?
it's for insurance purposes.
Oh.
If they have, and because the police are often, I'm told, the police are often trying to scam drivers. So what you're going to see is that it's going to be the meteorite is going to hit the top of the atmosphere. It's going to start glowing due to frictional heating at about, I think it's about 80 or 90 kilometers. It's going to come screaming down, and eventually the braking force as it's going through the atmosphere overcomes the strength of the rock. It's going to explode. There's a huge flash of light, and then one piece keeps going and makes a hole in a lake. And oops, that didn't work. And listen to the voices of the Russians, or the lack of excitement. Oh. So this worked just a second ago. Might have to call in.
The remnants of the meteorite out of the lake.
Okay, so here it comes. There it is. And And it gets to about 20 kilometers and just a little bit, and there's a big flash, and it breaks up. And then there's a last little piece comes down. And do you hear any excitement from the driver? I would be going crazy at this stage. And here it is again from a different viewpoint. Again. And one more time. And watch the people walking across the road here, if you can see them as it gets brighter. They don't even look up. I think they're there. Here they are. And the guy's just... And here's the hole that it makes in the ice. So they recovered, out of the 10,000 tons, they recovered less than a ton of that material. So most of it goes up in smoke in the upper atmosphere. Now, people did take notice about 2 minutes later when the shock wave from the explosion hit them, and about 1,500 people were slightly injured. But, these are supposed to be so once in 50 years or so. But as luck would have it, Siberia in 1908 was hit by an even bigger object, the so-called Tunguska event, which blew up completely in the atmosphere and flattened trees over 2,000 square kilometers. So that was a really dramatic thing. Luckily, it was in a totally unpopulated area. Now, the US is not to be outdone by the Russians, has its own even bigger impact crater in Arizona. It's a fantastic place. It's a Barringer crater. You can often see it if you're flying across the southwest from your aircraft. If you're ever in the area, you really should go and see it. If you're going to the Grand Canyon, do a little detour to this thing. It's really spectacular. So this thing came in with an energy of 650, not 30, 650 Hiroshima bombs, making a great big hole. Now, you know, these events are pretty rare. This is 50,000 years old. They're pretty rare, but nevertheless, the Congress was concerned enough that they had told NASA that they had to initially find all objects that are more than a kilometer across. Now, then they sent it down to less than more than 140 meters across by 2020. These are still much bigger objects than the objects that made this hole, for instance, or the Tunguska event. So we've still got a long way to go to really find even these things, which wouldn't be civilization ending, but certainly would hurt a lot. And even for 140 meter objects, there's estimated to be 25,000 near-Earth objects out there. So it's a hell of a task finding them. And if we have to go down to something like 50 meters, I don't know what the estimates are, but it presumably be of the order of 100,000 more objects. So it's a hell of a task. Now, NASA has also been tasked with figuring out what to do if they find a killer asteroid. As you might expect, some of the suggestions are better than others. But suffice to say, at the moment, if they find thank God that they haven't found, at least there isn't a killer asteroid out there that we know of, because at the moment we really have no idea what to do to deflect an object or break it up so that it doesn't do so much damage. Was there a question back there somewhere? No. And we don't have to go to Arizona if we want to see the effects or the influence of impacts. About 35 million years ago, a very large object hit just close to NASA Langley, actually. And in creating this large crater that was about 30, 40 kilometers across, it completely changed the drainage in the area and generated what is now known as the Chesapeake Bay. So if you like crab cakes and fishing or just messing around in boats, thank the rocks from space. And of course, the one that every human being has to be thankful for is the meteorite that hit the Earth in 66 million years ago and wiped out the dinosaurs and eventually allowed mammals to dominate the Earth and even later us to evolve. Certainly before then, we were definitely very much third-class citizens, or mammals were, I should say. Now, the Chicxulub crater in the Yucatan Peninsula is 180 kilometers across. That's a big pretty big, but it's not. It's only the third largest crater that we know of on the Earth. In fact, there are two much bigger craters. There's a 250-kilometer crater in Sudbury, which is a major source of nickel and copper for the world. And then there's the Vredefort crater in southern Africa, which, although it didn't generate a lot of mineralization on its own, what it did do is it revealed the gold-bearing rocks that are so crucial to South Africa's economy now. So they have some significant beneficial effects for human beings. Now, these two big craters are about 2 billion years old, and if you go further back in time, you would actually expect to see more craters and bigger craters, and we don't see it. And so the obvious reason for that is the Earth is a geologically active planet. So it's destroyed most of the really big impacts that happened early on. And if we're going to get some sense of how peppered the early Earth was, we need to go to the moon. Whoops. So as anyone who looks up at the night sky knows, the moon has some very big craters on them. One of the last and the largest is the Imbrium Basin. It's about 3.9 billion years old, and this is thought to more or less mark the end of what's called the late heavy bombardment. The late heavy bombardment was thought to have been caused by a major disturbance in the orbits of the giant planets that actually flung out Uranus and Neptune into their present orbits, so almost double their distance from the sun. And in doing that, all this sort of reshuffling of the orbits of the giant planets, they destabilized the inner edge of the asteroid belt, sending large objects into the Earth and the moon. Now, the Earth's gravity is its mass, and therefore its gravity is much larger than that of the moon's. So the Earth should have been getting both funneling more objects towards it and higher energy. So it should have had more of these basically sterilizing impacts. But we know within about 400 million years of the end of the late heavy bombardment, we have very good evidence for the existence of life on the surface of the Earth. So it was just waiting to happen. 400 million years is a blink in the eye, geologically speaking. It was just waiting to happen. Another thing to remember is that the moon itself is thought to be the result of a giant impact. And although there are many different ideas, the most conventional one that was a Mars-sized object hit the Earth, sent material into orbit around the Earth, and some of that later accumulated into what we now know as the moon. And here is a simulation of just one set of conditions from our current postdoc, Miki Nakajima. So you have here a Mars-sized object and an Earth, sort of proto-Earth. They've already differentiated into a metal core and a silicate rim or mantle. And just watch what happens to the
size of the proto-Earth. Is it the same size?
It's about 90% of the current Earth's mass. So just watch what happens to the core of the impactor. There's the mouse. It's unimaginably violent, these kinds of impacts. Notice how the core of the impactor is sort of streaming through the mantle of the Earth, and that this material around here that goes into a sort of orbit will ultimately at least some of it will reaccrete onto the Earth, some of it will become the moon. Unimaginably energetic events. So one of the important things, as I was pointing out, is that all this material, this metal that's streaming through the mantle of the Earth. And the reason I'm emphasizing this is that some elements just love to go into metal. So we would expect to see them all in the core. So all these highly siderophile elements, these actually very economically important elements like iridium, platinum, gold, palladium, should all have gone into the core during this last time when the core and the mantle of the Earth were able to chemically exchange with one another. In fact, I mean, the abundances are very low. They're about 100 times lower than the abundances would be expected from CI chondrites, but they're still much higher than we expect. And the reason is that after the moon-forming impact, there were more impacts bringing in fresh material that polluted the silicate part of the Earth. And the reason this is significant is two reasons. So it brought in an additional about 0.5% of the Earth came in after the moon-forming impact. And when we look in detail at the compositions of these things, they're consistent with the meteorites that are both dry and volatile poor. And so that would suggest that volatiles like the water, nitrogen, carbon, things that make life, the Earth, a habitable planet, were accreted before this incredibly violent impact that generated the moon. And I forgot to say another important aspect of generating the moon, having a moon that's orbiting the Earth, is it stabilizes the Earth's spin axis, so it doesn't wobble around. And it also, of course, gives us tides, which some people at least think may have played a role in the origin of life. That certainly was very important to early life. So I found when this became apparent, I found it quite extraordinary that these volatiles would be able to survive this sort of incredibly violent impact. But actually, you know, in reflection, perhaps we shouldn't have been so surprised, because my colleague Eric Howry has demonstrated that even the moon that was forming from this material that was floating around in space and at very high temperatures, even that was able to retain some water. Perhaps some of you came to his lecture a few years ago on that topic. But it does beg the question of where does the Earth's water come from? Where does the volatile nitrogen, the carbon, everything that we need to have a livable planet? And I'm afraid I have to have a quick detour into isotopes. So for those of you who don't remember your high school chemistry, atoms are made up of protons and neutrons. The number of protons an atom has basically dictates its chemistry, because it dictates how many electrons it has. But depending on how those particular atoms are made in stars, they can have different numbers of neutrons. So hydrogen has two isotopes, stable isotopes that is anyway. One is just made of one proton, one is made of a proton and a neutron. Actually, these were made in the Big Bang and not in stars. And then carbon has 6 protons and then variable numbers of neutrons. You may know that carbon-14 is a radioactive form of it that people use for radioactive dating of archaeological objects and human remains. And then nitrogen has 2 stable isotopes too, the nitrogen-14 and nitrogen-15. So as I said, isotopes have very similar chemical properties, but the heavier isotopes tend to concentrate in molecules that have stronger bonds. So you can fractionate one isotope from another, and that has some very important, or can be used as a tool to understand chemical processes that are going on both on the Earth and in space. And another important thing is that the fractionation of these isotopes between molecules increases as the temperature decreases. So I'm sorry, I'm going to have to get, normally we just show isotopes as ratios. Geochemists are always very looking for very small effects, and so they tend to like what's called the delta notation, which is basically the deviation from our standard, the Earth, in parts per thousand. So normally they're looking for very small effects, and that's gone on in, the cosmochemists use it too, although the numbers are much larger. But the important thing in this plot is that this is where the Earth's composition is in terms of hydrogen isotopes. This is the Earth's composition in nitrogen isotopes. Here is the bulk solar composition down here, a long way away from the Earth. So the Earth did not acquire most of its volatiles from the disk of gas around the sun. Here are the comets, which is another popular source of volatiles, and they're a long way from the Earth in the opposite direction. The only materials that really seem to be a good fit to the Earth, and not just in isotopes, but in abundant space too, are the CM and, again, our old favorite, the CI chondrites. So it seems like just 2 particular types of meteorite are the main sources of the volatiles that the Earth formed with. And that's not entirely unexpected, because when we compare the reflectance spectra of meteorites with what's out there in the asteroid belt, for instance, most of the objects look closer to the CM and CI chondrites than they do to other types of meteorite. But it still begs the question, how does this material, if it was originally in the asteroid belt, how does it end up in the Earth? And here is one simulation that actually, although it's a more recent one, goes back to simulations done by George Weatherall and John Chambers here at DTM back in the late 90s and early 2000s. So what we have here is we have Jupiter, it's already formed, and then we have color-coded lots of planetesimals in the inner solar system, starting from about where Venus is, out to Fourier, where the edge of the asteroid belt is. And they're color-coded according to their water contents. The assumption is that there's a thermal gradient in the disk of gas and dust from which these objects are forming, and so the ones that further from the sun form at colder temperatures and they acquire more water. And so here we see different time steps as you get this sort of stirring up by Jupiter of these bodies. They start to collide with one another, grow, and what you see is that things start to grow faster in the inner belt part where the densities are higher, and then gradually these water-rich objects get scattered into where the terrestrial planets are forming. So this actually, in many ways, is a very attractive way of making the terrestrial planets. But it has a few problems, one of which is that it tends to make Mars that's much too big. There are some other nitpicky things that people don't like either. And so people started to look for another way of doing this. And one way that they came up with is to clear out the asteroids, the planetesimals, that are roughly where Mars is now. So how do you do that? Well, the way they did that is to have Jupiter and Saturn move. So here's a simulation. It's called the Grand Tack, and you'll see why in a minute. Here's Jupiter. It's already pretty much formed. Here's Saturn. It's still growing. Here's Uranus, and here's Mercury. And if you know your distances to Mercury and Uranus, these are a long way in. Neptune, is out here, is here at about 8 AU. It's now at 30 AU. So things start to move pretty dramatically. And so here they've color-coded the small bodies inside of Jupiter, the so-called inner disk, and then outside of Jupiter. And what you can see is Jupiter is interacting with the gas, and this causes it to move. It starts to move inwards, and it starts to clear out all this material out here, just as the model needs. Saturn is growing. It starts to accelerate. It catches up to Jupiter. They get locked in a resonance, and for reasons that I'm still don't really understand, that changes the way they interact with the disk, and they move back out again. That's the Grand Tack. And they keep moving outwards, pushing Uranus and Neptune out as they go, until the gas disk dissipates, as it has to do at some point. And then everything stops. And you can see what happens is, initially you scatter all this material out of the inner disk, and then as these things move out, they scatter some of these blue points into the inner solar system. And these are coming from the outer solar system. Things are cold. They should be full of ice and dust and stuff, and so they could be very potent sources of water. And you can see, I hope at least close here, you can see in the proto-asteroid belt you have a nice mix of red dots from the inner solar system and blue dots from the outer solar system. And it's a very attractive, I find it very attractive to have Jupiter and Saturn marauding around the early solar system, causing havoc. But as a scientist, we should try and test it. And theorists are very creative people. They can always come up with interesting ideas, but it's the duty of our experimentalists to then go and test their theories. So how would a meteoriticist test a model like this? Well, we're getting samples from the asteroid belt. Can we find a way of telling whether they formed in the inner solar system or in the outer solar system? And that's a very tricky thing to do. But one of the ways you might be able to do it is to use, the hydrogen isotopes in the water. Now, when the solar system formed, it formed from a molecular cloud, and the ice that it's inheriting from the molecular cloud is known to be very deuterium rich. So very rich in the heavy isotope of hydrogen up here somewhere. But if things get hot in the inner solar system, that water is going to evaporate. It's going to be able to react with the hydrogen that has a solar composition, and it's going to become very isotopically light. And then there is all sorts of mixing processes in the disk at the time that these objects are forming that are going to mix the stuff, the heavy stuff in the outer solar system with the light water in the inner solar system, and you get this sort of gradient. And this is just the gradient of the hydrogen isotopes in the water over the hydrogen isotopes in the hydrogen gas that dominates the disk. And what you get in this very simplistic model, overly simplistic model, is a gradient. And in fact, although we don't really know where comets formed, they're sort of consistent. They're consistently deuterium-rich and more or less consistent with where we think the comets formed, somewhere beyond 20 to 30 AU. So, can we find evidence for very heavy water in the meteorites if they're forming from similar regions or regions in the outer solar system, particularly those that may form where comets form? So this is a sort of rejigging of what I just showed you, but this is real data. So here we have comets. We don't really know where they are, so I've just sort of stuck them at 20 and 30 AU. Two different flavors of comet. You don't really need to know. I'm happy to explain if people want to know what these different types of comet are. And these are direct measurements of comets. So they're all very deuterium-rich relative to the Earth and certainly relative to the solar value. This is Enceladus's Saturn. This is Enceladus, Saturn's moon, in its present position, although during the grand tack model, Saturn would have been in this region here, somewhat further in. So if Enceladus was forming as Saturn was going towards the end of its growth period, actually Enceladus should be here. So perhaps you can, it seems like it was fairly, the gradient in, or lack of gradient in deuterium to hydrogen ratio in the water was fairly flat at this point. But then when we look at the meteorite water, it's way down here, well below the Earth's water composition, suggesting that these meteorites probably didn't form much further out than where we see, certainly not any further out than where we see Saturn today. This is a potential problem for the grand tack model. It's certainly not a killer blow for the grand tack model. I could show you a plot for nitrogen isotopes. You get the same effect. The take-home message is that the chondrites don't look like they formed as far out as the grand tack model might predict, but I'm sure there are ways that one can tweak the grand tack model to be able to get these results consistent with what we're seeing in the meteorites. Now, switching subjects, I hope not too quickly, I promised to explain to you why there was a lot of radioactivity in the early solar system. And we know from measuring meteorites that there was all sorts of short-lived radionuclides. These are radioactive isotopes that decay on timescales of less than 10 million years. And they're all made in stars, primarily in supernova. So the problem is, since these are things that are decaying, in many of them in less than 1 million years, you have a very little time between when you make them in the star and getting them into the solar system and then into planets to do the melting that we see. So the original idea for this was that, in fact, a supernova caused the molecular cloud where the solar system formed to collapse. So the shock wave from the supernova hit the molecular cloud, compressed it, and it started to collapse. And it's still a viable option because that way, you're pumping freshly made material into a forming solar system very soon after it's made. And Alan Boss, one of my colleagues, has demonstrated that this, in fact, is a possible way of doing it. The trouble is that, in general, it's thought that stars form not as isolated objects as this might expect, and this will be not a one-off, but it will be a rare event. People think that planets form, or I should say that solar stars form in clusters, in molecular clouds, in big clusters. And so, some of those can be very massive stars in these clusters. So there's an idea that is becoming more and more popular, that in fact what's happening is that you have a molecular cloud, you make a bunch of stars, some of them are very massive, they evolve very rapidly to become supernova, they eject their radioactive materials into the molecular cloud so that the next generation of stars that form from that molecular cloud are polluted with this material, and so on and so on. The great attractiveness of that model is that it would suggest, which most scientists like, is that we're not special, that we don't need fairly special circumstances, but this is a very general process that most stars would form, or most forming star systems would experience. And they would also inherit a lot of radioactivity and differentiate into core and mantle. And rather surprisingly, we have some pretty good evidence that this is in fact the case. And it comes from a very surprising source. Before I get to that, so as I said before, you have radioactivity that melts these forming planetesimals. They differentiate into metal-rich cores and silicate-rich outer mantles. These get busted up by collisions, and so you will have various proportions of iron to silicate material in these fragments of the meteorites, of the planetesimals. And we see this in the asteroid belt, but we also see it, somewhat surprisingly, around white dwarf stars. Now, I should quickly explain. A white dwarf is the core of a star that has reached the end of its life. It's blown off most of its envelope. It's stopped doing any nuclear burning. So it's just sitting there slowly cooling. But they're actually very good for doing certain types of observations. And one of them is because they're basically just have very clean spectra. And so what seems to be happening around some white dwarfs is that they had indeed planetesimals that got busted up, and they are falling onto the star. And when they fall onto the star, for about a month or two, they give off enough light that you can measure the compositions of the material that's fallen onto the star, onto the white dwarf. And what one sees is that one sees a material that has a range of isotopic compositions of silicon to aluminium and iron to aluminium ratios that are entirely consistent with stuff that's dominated by metal up here and stuff that's dominated by material that looks like typical volcanic rocks down here. So it looks like you've had a star system that's reached the end of its life, it's blown off its envelope, presumably that's destabilized the orbits of small objects that are then eventually go crashing onto the surface of this star, and you can measure their compositions. And it looks like that they have differentiated, and therefore they acquired radioactivity just like we see in the early solar system. I would never have guessed this was the one way we could actually not necessarily confirm, but certainly have consistent data with what we've been saying from the meteorite literature for some time. Now, supernova don't just make radioactive materials, they also make dust, lots of dust. But there are other types of stars that also make dust. These are actually the progenitors for white dwarfs. These are so-called asymptotic giant branch stars. They're dust factories. They come from stars that are smaller than that become supernova, and they take a longer time to evolve. So unlike the supernova, they're not near where they were born. When they die, they get scattered throughout the galaxy, spreading material as they go. So one of the ideas when we were looking at meteorites was, can we find the dust associated with a supernova that may have triggered the solar system, or that may have polluted the progenitor cloud from which the solar system formed? And indeed, we do find dust from stars. And how do we know that they're coming from stars? I should say that we find these things are sort of graphite. These are scanning electron microscope images of these dust grains. That's about 1/1000 of a meter across. These are huge by astronomical standards, I should say. This is graphite, silicon carbide, where I find diamonds that are 1,000 atoms in size. We find silicate grains. We find a whole cornucopia of different materials that came from dying stars. And we know they come from dying stars, again, from their isotopes. But there's nothing subtle about the isotopes in these objects. As you can see, so here's the solar composition for carbon, here's the solar composition for nitrogen in absolute ratios now. And instead of talking about percent or parts in 1,000 or 10,000, which most geochemists do, we're now talking about factors of almost 10,000 in the isotope ratios. The only way you can do this is by nucleosynthesis in stars. Chemistry, physical, and normal physical process simply won't do it. And so we have these carbon, nitrogen, we can measure oxygen isotopes in the oxygen-rich types of grains. The two important things that we see is here. We don't see an overabundance of supernova dust. So it's certainly, that doesn't kill the single supernova idea for making the solar system, but it's not, it certainly doesn't make it very attractive. And we also see dust from very large numbers of stars. In fact, what we can do with these large numbers of stars that form from different mass stars that form at different, that may take millions to billions of years, and so go back for a very long time in solar system history, in galactic history, is we can use these stars to understand how the elements were built up from after the Big Bang in the galaxy over time. And I find that an extraordinary thing to do, that you can measure something that's a millionth of a meter across to say something about how the galaxy evolved. If people like big numbers, that's something like 50 orders of magnitude, or 1 with 50 zeros in front of it. A difference between the mass of a small 1 micron grain and the galaxy. Now, when meteorites don't just have pre-solar grains and these objects that come that sort of date from the very earliest time of the solar system, they also have organic material, which has made them very interesting to people who study astrobiology and the origin of life in our solar system and potentially other solar systems. The meteorites have a very complex soup of organic materials, or compounds. So at least thousands, maybe tens of thousands of different types of organic molecules are present in some of these primitive meteorites. Most of them are of very low abundance, which is a problem, which I'll come back to. But the thing that really catches people's eye who are interested in the origins of life is that they have over 80 different types of amino acids. Amino acids are one of the fundamental building blocks of us, of proteins and things. And they're thought to form by simple reactions involving simpler molecules, and hydrogen cyanide and ammonia. But the thing that really catches people's eye is that some of them are chiral. That is, they have, I'll come back to what chiral means, and in particular, they're left-handed. And the reason that's very exciting is that life is left-handed. And what do I mean by left-handed? So chirality, or handedness, is a characteristic of most of life. Now, in this example here, you can see, so if you held up your hands, they are mirror images of one another. You can't actually superimpose them physically on one another. You have to put a mirror between them to be able to superimpose them. And that is true for certain types of molecule as well. It was discovered by Louis Pasteur. And correct me if I'm wrong, but as I understand it, life is typically left-handed in terms of, at least in terms of its amino acids, because for proteins, it needs to do a lot of folding and generating very, very specific shapes for the active molecules. And you can't do that if you've got different things with different structures. You need to have something that's very consistent. And so, for reasons that are still unclear, it decided to be left-handed rather than right-handed, because and that is still a big mystery. If people find this is all too so esoteric, something that might bring this home is the importance of structure, is that the scents of lemons and oranges come from the same molecule. They just are left and right-handed. And that is also true for mint and caraway. I discovered this yesterday when I was doing some research. I had to share it with you guys. So the important thing is that handedness really is important. And normally in non-biological processes, you have an even number of the right and left-handed. And so the thought that some people have is that the meteorites were delivering this slightly left-handed amino acids, and that this gave life the little kick it needed to become left-handed rather than right-handed. One of the main problems is that there's not an awful lot of organic material in the meteorites, and so many people would say, look, you can make this stuff much more easily on Earth. they haven't actually demonstrated that yet quantitatively, but I think at the very least, the meteorites are telling us there are ways, physical, non-biological ways, for preferentially producing left-handed over right-handed things. And if we can figure out what happened in the meteorites, we might be able to figure out what happened on Earth. Now, these sort of amino acids and things are actually a minor component of the organic material that in meteorites. Most of it comes in a material that's more like coal. It has these large, isotopes, again, deuterium and nitrogen-15 enrichments. It's thought to be an indicator of formation in a molecular cloud, perhaps in the cold outer part of the solar system. It has a composition here normalized to 100 carbons that's almost identical. This is the meteorite composition. This is the composition of Comet Halley. And recent measurements of the Comet 67P also suggest that the organic material in that comet is very similar to what we see in meteorites. And although this is not really relevant to this talk, I had to show this lovely set of photographs. So one of the things these mysterious things we see in the organic material in meteorites are these little balls. They can be tiny, less than a millionth of a meter across. One of my colleagues was able to separate one of these out, put it on a sample holder, and then using a focused ion beam, slice it in half, and was able to demonstrate it was hollow, truly hollow, which people had suspected, but this was the first really clear demonstration. It was truly hollow. There was nothing in it, no minerals, no water, nothing like that. I just think it's a fabulous technical tour de force, even if it's scientifically not the most interesting thing. But the origin of this organic material is absolutely fascinating, and I suspect it could be just as important for the origin of life as the amino acids and things. But it wouldn't have been delivered in big objects, because big objects hit the Earth at 20 kilometers a second, then they vaporize. It's going to be coming in primarily in dust produced by the grinding up and collisions of the asteroids in this very, very early solar system, or comets indeed. And we still see some of this dust coming into the Earth today. Most of this material is collected in the upper atmosphere. Because it's very fluffy and it slows down very slowly in the upper atmosphere. It does get a little hot, but not too hot. And if you fly a modified U-2 spacecraft, a U-2 spy plane up in the upper stratosphere where there's not much terrestrial dust, and put out little collectors underneath the wings, you can collect this stuff, which you can use to study. But it's very small, and very small amounts of material come back. And these flights don't happen very often because they're expensive. Now, these objects come from asteroids and comets. As I said, we're going to be getting a bit more asteroidal material back in the next 5 or 10 years, but comet return isn't going to happen at least till the mid-2030s, and maybe much later than that. So I'll be long retired. So how can we get hold of more of this material to study the organic material, the pre-solar grains and stuff, and compare it to meteorites? Try and understand what comets are made of before we actually bring any back. And this is why some colleagues and I came up with what we like to unofficially call the cosmic dust buster. The air in the South Pole is extremely clean, and if you point a collector into the wind, you should, if we're lucky, not only, but should be collecting mostly dust coming from space in this region. And so here, this is the experiment. It's actually the principal investigator is a woman called Susan Taylor, but Larry Nittler and myself are heavily involved in this, and we actually have the first samples we brought back earlier this year sitting on my desk waiting to be opened and looked at. But basically you have this inlet facing into the wind, the prevailing wind direction at about 6 meters off the ground, so you don't get a lot of blown snow. And basically it's just pulling air through a filter and filtering out everything that's more than 10 microns across. And the hope is that we will be bringing back hundreds and hundreds of particles, maybe thousands of particles every month. It's much cheaper than a U-2 spy plane flight, and it would be going basically 24 hours a day, 365 days of the year, except for storm days. It's running at the moment, and I would also say if anyone ever gets the opportunity to go to the South Pole, go. It's an absolutely fantastic place. So, I think it's time to wrap up. I love this New Yorker thing. So I hope I've shown you that we should be grateful to space rocks. Not only did they wipe out the dinosaurs, but they brought the basic building blocks that we need for a habitable planet. And occasionally they make things like the Chesapeake Bay, which we all benefit from. The meteorites and the dust particles I was talking about come from a large fraction of the solar system. And so we're really able to interrogate what was happening in the various processes were happening in the early solar system at the time before and during the time of planet formation. And because, as we saw, the aluminium-26 story seems to be true not just for our solar system, but for other solar systems around white dwarfs at least, we think that what we discover from meteorites and from interplanetary dust particles it applies not just to our solar system, but as it may be more generally applicable to the way solar systems and planetary systems form. And just to reiterate that the meteorites are a fantastic scientific resource, and that we're able to address issues from the processes that of element formation in stars and how those stars evolve, to what happens in molecular clouds, to what happens in forming solar systems, and so on to the formation of asteroids and the delivery of those asteroids from comets and meteorites. Thank you. And I completely forgot. I meant to pass around these samples of a meteorite, but if anyone wants to hold the oldest thing they're ever likely to hold, please come to the front after the talk.
We'll take some questions.
Why do people collect meteorites?
Why do they collect stamps? You know, I think because they're rare, or at least some types of rare, and they're exotic. They come from space.
No scientific
Oh,
purpose in collecting.
the collection.
I'm not talking about the people who go out and find them.
No, the collectors generally are not scientists. What they will do is they will, or actually, more often the dealers rather than the collectors. What they will do is that they will give a certain amount to science so that we can authenticate that there is a particular type of meteorite, and we can use that fraction for scientific purposes. But collectors are collectors. You know, they just like to have beautiful things in their collections, and some meteorites really are beautiful. Okay. Yeah, something like that.
That's just words. Now, as the chemistry life, there was a talk given at Goddard a while back, which I think was unaware of what I think is a very essential area of chemistry. Oh, I think is not very active. Ion molecule chemistry.
Yes.
Given an ion, either molecular or atomic, it's got a charge. And given a neutral molecule, there is an attractive force because the charge polarizes the
Yep.
neutral particle. And the reaction rates are enormous
Yep.
compared to neutral.
Yeah. So two things. Yes. So I think meteorites and meteorology all come from the Greek word, and certainly even the Greeks recognized that meteorites came from somewhere up there, but they were thought to be atmospheric phenomena, not from space, except for this Diogenes. So yeah, ion molecule chemistry is extremely important in the interstellar medium, where temperatures are very cold, and so. Well, it's for galactic cosmic rays do most of the ionizing in interstellar medium, and the reason it's important is that these very low temperatures, there's not enough energy in the molecules to overcome activation barriers. But the ion molecule reactions have very low activation barriers, and so you get these reactions going at 10 degrees above absolute zero. Right. Yep. So I think the only time that neutral-neutral reactions are important, at least in molecular clouds at 10 Kelvin, is on the surfaces of grains. but that's not really my field of expertise.
Question back here. Way back.
How do you distinguish between
Okay. So generally, this dust here is made up of a very complicated mix of materials. Actually, one of the simplest, biggest giveaway is if you see nickel when you do an analysis, a non-destructive analysis in an electron microscope. If you see nickel there, it's almost certainly an extraterrestrial object. But you know, it's their fluffiness, the very complex nature of them. They generally have a lot of organic material in them. All those things are very characteristic. The typical terrestrial dust that we see in that area is sort of blocky, single grains. It doesn't look anything like an extraterrestrial material.
There in the back.
I've heard that moldavite was a or exoplanetary mineral. Is there another example? Is there any proof of that statement? Is there any example?
I know moldavites are a type of rock.
The tektite.
Tektite,
It's
yeah.
It's a group. It's a type of rock known as tektites, which is generally interpreted the impact melts on the Earth.
Yeah.
So when you have an impactor into the Earth, some of that material gets splashed up not in orbit, but into the atmosphere. It's molten. It cools quickly in the atmosphere and forms these glass objects like moldavites and
Australites.
and the whole families of these that are usually associated with impactors. So the wisdom is it's basically just melted surface rocks.
Of the Earth. So they're not specific minerals, but they're sort of basically glass.
Sorry.
Of the meteorites that you have examined, have there been any electromagnetic properties exhibited from any of these?
So generally not, but there's recently, with improvements in techniques, people have started to measure the magnetic properties of meteorites. Some of them, it looks like they come from bodies that had dynamos, just like the Earth. Some people are skeptical about this, but you know, there's more than one group have now seen this and claimed that they find evidence for magnetic fields existing in early differentiated bodies. And I think that's an extremely interesting thing. I'm not sure people understand how such a small body could generate a dynamo, but it seems to be the case. So yes, people are starting to look at it now with these new superior techniques. The effects are pretty weak. But so that's what we're going to start learning with these. So you get this big filter back, and then you've got a few hundred particles that are only 10 millionths of a meter across that you have to then find on that filter. So that's going to be quite a bit of patience. We think we can do that. Then you're going to have to pick them off and put them onto sample mounts that you can then go and put in some of our expensive and very temperamental toys. It's going to be painstaking work, at least initially, while we develop the techniques. But it's better than waiting for 30 years or so, 25 years before the samples come back from a comet. So, yes. Depends what size you're talking about. I don't want to scare you, but in total, there's something like 30 or 40,000 tons of material is hitting the Earth every year. Most of that is dust, shooting stars and things like that. Some of it comes in bigger stuff. I was going to show you, there are actually some interesting things if you go to Wikipedia, which will show you some of the bigger events that are detected, actually using equipment developed for detecting nuclear explosions. So there's meteorites falling all the time on Earth. Most of them fall into the oceans, unfortunately. A lot of the other ones fall into areas where either there aren't any people or they're hard to find and they're not seen. So I would guess every year 5 meteorites are seen to fall and picked up. I don't know, that's just something off the top of my head. Not a lot, But yeah, if you ever see one, it's very exciting.
There's an old story that if you park your car, not here where there's all sorts of pollen, but if you park your car out in some place for a week, and then you go and you keep all the dust off it, these 2 or 3 dust particles are
Meteorites that are picked up and if they're attributed or the sources like Mars, how would you know?
So there was several things. One is, unlike, small bodies cool off very quickly, so they tend to, so the small bodies from the early solar system all give very old dates. But back I would guess in the 70s, people were finding a few meteorites that had very young dates, and they were 100 million years or something, a few 100 million years. But the real clincher was, so they thought it had to come from a big body, but they weren't quite sure why. The real clincher was the measurements of the atmosphere of Mars by the Voyager, wasn't it? It was the Voyager spacecraft. So they measured the elemental composition of Mars's atmosphere, and when some people went to measure these objects that they suspected came from Mars, lo and behold, in some of the glass, they discovered the glass had exactly the same composition of material trapped in it to the Mars's atmosphere, and I think that's been the clincher. And now, we've found, I think there's 40 or 50 meteorites that we're almost certain come from Mars. And so there are many different types of evidence, but the atmospheric gases trapped in these Martian meteorites is the clincher. There's a big impact on Mars, and then they get scattered. Some of that material makes it off Mars, and then they get scattered towards the Earth. I mean, another amazing thing is you can actually find some of these rovers have actually found meteorites sitting on the surface of Mars, so we know there are impacts even there today. So the amino acids and things, sure, you can make them on Earth, no problem. It's more complicated making this the sort of what I said was coal-like material that is the major carbonaceous material in meteorites, and we think in the dust particles. That's more difficult to make. It's not from coal. It's clearly formed by abiological processes, and we don't have any evidence that those processes were happening on Earth. But it doesn't necessarily mean that that's a good reason for why we think these things had a role to play with life. That's absolutely right. But it's clearly there's something different was happening in the meteorites than was happening on the early Earth.
Would the moon be a real good place?
No. That's because it doesn't have an atmosphere to slow them down, so they just slam into the surface of the atmosphere and vaporize. They have evidence for in the soils that they brought back from the Apollo missions. They have evidence for little bits of vaporized and recondensed or tiny little fragments of meteorites. But in terms of looking for intact meteorites, no, it's not a great place to look.
You can see the chemical signals in this plot that Conel showed of the cinerophile elements like to go into the core. The way that you can tell melt on the moon is impact melt, because those elements are raised. They're raised because they're the meteoritic component. But the chemical component now is not anything left of the meteorite other than this chemical.
It's primarily it's just slowing it down, and in that process it gets very, very hot, which is why you see this bright white light. So you're vaporizing a lot of the rock in this process. It's like air braking, but under very extreme conditions. The same way, a re-entering spacecraft uses the atmosphere to slow down. Unfortunately, the meteorites don't have parachutes so you have this enormous amount of kinetic energy that they have when they hit the atmosphere, and you have to dissipate that somehow, and the atmosphere is doing it. Yeah. I don't think so. the meteorites do modify the Earth's the chemistry of the upper atmosphere because you have all this material that's being, particularly actually it's the dust more than the solid material. Shooting star is this stuff burning up at 70, 80 kilometers up in the atmosphere, and they deposit a lot of material in the upper atmosphere. And in fact, they're the dominant source of things like sodium in the upper atmosphere. So they definitely affect the Earth's chemistry. I don't know whether they will change the Earth's chemistry in any dramatic way if, for instance, you have less or more of this material. It's beyond my expertise.
Back there.
Are there any experiments in the International Space Station?
I think at the very early stages, I can't remember if it's actually got funded, there was a proposal to have a dust collector on the space station. I think it did fly up, and basically it was a series of layers of very thin aluminium, I think, I can't remember. And so the idea was that these particles would come through, and rather than hitting the atmosphere, they'd be going through all these multiple layers of aluminium and slow down sort of vaguely slowly, that some material might survive. I don't think much came of that experiment. People are certainly concerned with impacts on the space station, but most of the stuff that's concerning is actually not from extraterrestrial, but it's man-made debris from rockets and satellites and things.
Just a couple more, one in back.
Yeah.
Go ahead.
Well, I guess that's the whole point of the NASA program at the moment. Hopefully, it's not on a direct collision course. I think if that was going to happen, we'd probably only have months. I think what they're trying to do is to map out the orbits of all large asteroids, and then they can estimate if they're ever going to be on Earth collision orbits as they evolve. So hopefully we would have many years to worry about them and not months, because months would be a disaster.
There was a meteorite recently, 2 or 3 years ago, on the sea.
Yeah.
That was seen
2 days beforehand.
So it was seen by telescope 2 days before it impacted. They predicted the orbit, knew exactly where it was going to go. It landed in Somalia.
Sudan.
And they predicted exactly where it would land in Sudan. They, so they gave this line on the Earth where you should go look for this thing, and the team went and looked for it, and they found it exactly.
Yeah.
So you can see these. Now that was a pretty small object.
Yeah.
I mean,
Yeah.
basically little stones like this strewn around the ground by the time it got to the Earth. So if they're good enough for that for 2 days, maybe it's better or something else.
So I'm told there are some blind spots where it's very difficult to see the meteorites. In fact, the Chelyabinsk was not seen by any telescopes and was a complete surprise. And that was a 60, much bigger than the Alma-Hattasita one. So it's a bit hit and miss at the moment.
Here, and then we'll take the one back.
I noticed that you said something was coming in at 20,000 miles an hour. So I know the escape velocity of the Earth is 25,000 numbers.
Yep.
If you had something coming in based on Earth's,
Gravity, right.
it would only be going 25.
Yeah.
The extra 10 or 15,000 miles an hour, is that coming from
It's got to have something to do with the particular orbit it was on when it collided with the Earth. I must admit I haven't gone and really checked the numbers that I looked up, but that seems to be the consensus opinion. It was somewhere around 20 kilometers a second or 40,000 miles an hour.
Last question, right there.
In all of your years and your career,
You make me sound very old.
with all this great research and all of your experience in this field, what have you come to learn about the origin or nature of the world that we live in? Like, what did you take away?
Well, I could give you a whole nother lecture. I think actually it's the randomness of it all. You know, what would have happened if there hadn't been the Chicxulub crater that killed off the dinosaurs? What happens if conditions have been slightly different, if the grand tack model is correct, if conditions have been slightly different, and instead of Saturn catching up with Jupiter and turning around, it had just gone flying in towards the sun and scattered everything, there wouldn't be any terrestrial planets at all. And I think that's something we're learning from studying the exoplanets, like my colleague Paul Butler finds, is that there seems to be no set type of solar system. Every single solar system people look at are different. So clearly there's a very chaotic element to formation of solar systems, including our own, at least as far as we know it with our primitive understanding at the moment. And I think that's the real takeaway, is how chaotic the universe is and how lucky we are to be here at all.
Let me remind you that the next neighborhood lecture is on the 25th of May. It's by Andrew Steele of the Geophysical Laboratory. It's titled Mars, Moon, Missions, and Microbes, Life as We Don't Know It, and How Do We Find It? So we hope to see you back here in May.
It's nice to see a neighbor.
Hi.
So you can pick it up. So the white things that you see in here, if I had my glasses out, the white things are these inclusions that are the oldest things we know of in